Hi, and welcome to our last online discussion. So per popular request, I'm going to talk about the second derivative test that's been covered last week. So here's the exact statement. Suppose f from R2 to R has continuous second partials. And suppose that the first partial with respect to x at point AB and the first partial with respect to y at the point AB is 0. It means that the point AB, f has a critical point. So in order to state the full theorem, we need a definition. So for such a f, the Hessian is the matrix that's 2 by 2 and has the form HF equals fxx, fxy, fyx, fyy. Then we have these three conditions. So if the determinant of the Hessian is positive and fxx at the point AB is also positive. Here, of course, I evaluate my Hessian at the point AB. So if the Hessian at the point AB is positive and fxx at the point AB is also positive, then FAB is a local minimum. And for the second case, if the determinant of H at AB is positive, but fxx at AB is negative, then F has a local max. Third case, if the determinant of the Hessian at the point AB is negative, then this point is a saddle point. Great. And here is the reason why this theorem works. So since f is of class C2, so C2 means twice continuously differentiable, which is basically our assumption that all the second partials are continuous. So this is C2. And for C2 function, we know we have the second order Taylor expansion. Which gives, let's expand at the point x naught equals AB. We have f of x is roughly equal to f of x naught plus the gradient of f at x naught dot product with x minus x naught plus 1/2 of x minus x naught transpose h times x minus x naught. So this is basically your f prime times x minus x naught. This is your first order or linear term. This is your f double prime times x minus x naught squared. This is your second order or your quadratic term. But we know by assumption the gradient at x naught is 0, right? Because this is a critical point. So we have that fx minus f of x naught, this difference is controlled by the quadratic term only. Right? And this basically explains why we have a Hessian here, because the Hessian is the multivariable version of the second derivative. And likewise, in the case where we have a regular function from R to R, the second derivative controls the concavity, right? So if my second derivative is positive, it concaves up, and so at that point I have a local min. If the second derivative is negative, then it concaves down, so I have a local max. And here exactly the same thing is happening. But then we need to show it rigorously. So here's the definition. A n by n symmetric matrix A. So symmetric means A transpose is equal to A. Such a symmetric matrix is called positive definite. If and only if for all vectors x in Rn, we have xtax is larger than 0. Of course, my x needs to be non-zero. So notice that our Hessian here is also symmetric. Why? Because we assume the second derivatives are second partials are continuous, and since the second partials are continuous, we have fxy equals fyx. So the terms on the diagonal are actually the same. And you can show that a matrix A is positive definite if and only if all eigenvalues of A are positive. Great, so let's now bring our focus back to our Hessian. So, first case. Suppose H, the Hessian, at the point AB is positive definite. Then I know x minus x naught transpose H, x minus x naught, is going to be larger than 0 for any x in R2, just by definition. But by Taylor's theorem, this thing is exactly equal to the difference between fx and fx naught, which means if the Hessian is positive definite, then for all close enough x, I need to add here for the Taylor's theorem, we're assuming that x is close to x naught. So here, for all close x, close meaning maybe in a disk within x naught, fx is going to have larger value than x naught, right? This is approximately equal, which means fx naught here is going to be a local minimum. It's a local min, and maybe perhaps not a global min, because this Taylor expansion only holds for x that is close enough to x naught. So this means the graph of f is a cup at x naught. Second case. Now suppose h is negative definite. So negative definite is exactly the same definition as positive definite, but then instead of larger than 0, you just put less than 0. So it means x minus x naught transpose h x minus x naught is less than 0 for all x in R2. And again, by Taylor's theorem, this is approximately equal to fx minus fx naught for all x close enough to x naught. And therefore, fx naught is a local max. And so the graph of f is a cap at x naught. Third case. So case 1 corresponds to h having all positive eigenvalues. And negative definite corresponds to h having all negative eigenvalues. The third case, we consider what if it has some positive and some negative eigenvalues. So h has both positive and negative eigenvalues. What does this mean? So eigenvectors of h give the principal directions. Of f. It means if I slice the graph of f along one of these eigenvectors, I will get a parabola. And the associated eigenvalues control the concavity of f along the principal directions. So it means if my eigenvalue lambda is larger than 0, then at that principal direction I have concave up. If my eigenvalue is less than 0, then I have, in that principal direction, concave down. If my eigenvalue is 0, then it's locally flat. So if I have both a negative and a positive eigenvalue, it means if lambda 1 less than 0 and lambda 2 larger than 0, then one direction I have concave down, and another direction concave up. Right? If you can imagine what it would look like, so in one direction I have concave up, the other concave down, right? So this would be indeed a saddle point. So this finishes our third case. And notice that if neither case 1, 2, nor 3 happens, then the second order test is just not conclusive, which means you need higher orders of Taylor expansion. Now, let's see how these three cases connect to our clauses A, B, and C in our original statement. So let's recall the determinant of H is the product of the eigenvalues, but we can also explicitly calculate it to be fxx fyy minus fxy squared. And we know the trace of H. So the trace is the sum of diagonal elements. So it means my Hessian is fxx, fxy, fyx, fyy, then the trace of H is just this plus this. So it's fxx plus fyy. And the trace, we know from linear algebra, this is equal to the sum of the eigenvalues. Great, so in case A, remember we had positive determinant and fxx larger than 0. Since the determinant is positive, it means the product of the eigenvalue is positive. So lambda 1 and lambda 2 have the same sign. Right. And I also know that fxx and fyy is positive. Therefore, fyy must be larger than 0, because by assumption, fxx is larger than 0, and fxx, fyy, they must have the same sign. So this conclusion is reached by just considering this equation. If this product is negative, then we have a negative thing minus something squared, which is surely negative, but the determinant is positive. Great. So I now know the trace of H, which is fxx plus fyy, is positive. And so this means lambda 1 plus lambda 2 is positive, and they have the same sign. And so lambda 1 and lambda 2 must both be positive, which means H is positive definite. So this is my first case. In clause B, I have determinant h is positive, but f(x(x) is negative. Again, because determinant is positive, lambda 1, lambda 2 have the same sign. But I also know that determinant is f(x(x), f of y minus f(xy) squared is positive. So it must mean f(x(x), f(xy) is positive. So they have the same sign. And since f(x(x) is negative, I have f(y)(y) is negative. And so the trace is negative. The trace is the sum of eigenvalues, so each eigenvalue must be negative. This is h. This means h is negative definite. So this lands in case 2. Now for C, determinant of h is negative, which means lambda 1 times lambda 2 is negative, and so they have different signs. So lambda 1, lambda 2, different sign, which means one is positive and one is negative. So this is case 3. And now we have proven our theorem.